presentation, we're going to apply the LCPC transform to analyze rock shapes. That is the shapes in power scale of roundness. And we're going to do this to show the depth of information that we can obtain through our technology by measuring shape without measuring area or volume. So power scale of roundness is a semi-quantitative method for a geologist or sedimentologist to assess the shape of rocks. That is 3 particular features. Okay, that is its sphericity. Okay, its angularity, that is how jagged it is around the edges. And its roundness, how smooth its edge is. So we have applied the LCPC transform to these very shapes, these iconic shapes on power scale of roundness, to show just how much more information we can extract. Quickly, how we did that was we first created a mask representing the outline of each rock. Then we calculated its centroid. And in step 2, we then defined the centroid as the center of the radial grid, a 360-degree grid in which radial lines were spaced every 5 degrees. Next, we calculated the distance between every intersection between the grid lines and the object. Right? We calculated its distance to the center. Thus, we have the image in step 3. And next, we linearized this shape so that it's on a linear scale. On the x-axis, it's degrees starting from 0 and all the way to 360 on the right. And next, we applied the fast Fourier transform on the data in step 4 to get the frequency plot in step 5. And this frequency plot is a multi-dimensional representation of the original shape. Right? We've quantified this shape, right, in this set of frequencies. And if you want to derive a one scalar value, that is one number that represents the shape, one method is to sum all the bins, all the magnitudes in all the bins to get one scalar value, right? One number that represents the original shape. So that's how we did it. And here are shapes A through F, that is the high sphericity shapes. And as you can see, each has a distinct frequency spectrum. And general patterns are that the smoother the edge of the rock is, the smaller the magnitudes, or smaller the magnitude bars are. And another theme is that for shapes like in B and C that are not radially symmetrical, right? You see these last 3 bins, right? They're very high, okay? Because here, if you look at F, right, it's the ones that nearly a perfect circle, or very smooth edge, where you have very small values for the last 3 bins. Here in A, right, you have a jagged edge, but it's relatively, the jaggedness is relatively uniform around the whole sphere or the whole circle, okay, and therefore these last 3 bars are, you know, in this lower range. If you look at B and C, right, it's clearly not radially symmetric because there's a protrusion here, and this one looks like there's a protrusion on this end and this end, and so it looks like the pattern is that when the object is not radially symmetrical, the last 3 bins, right, are the largest. Next are shapes G through L, which are the shapes that are non-spherical, they're elongated. And the same theme as before, the more jagged the edge is, okay, that is the more angular the edge is, the larger these magnitude bars are compared to the smooth oval here. And similarly, the more asymmetrical the object is, the larger its bins are, right, in the last few bins here, okay? And to summarize, here are the 4 extreme ends of the objects, okay, and comparing these 3 features on power scale of roundness, or that is roundness, sphericity, and angularity. We see that for objects that are circular in shape, notice that the magnitude bars are all a lot smaller. Okay, notice the scale here. All right, 600 here, 1,000, and we modified it to show enhance the effect of scale. Right, and you can see that each shape can be distinctly quantified. It can be represented through this multi-dimensional manner. And lastly, it is possible to have one scalar value representing each object. Here in panel M, we just summed all the magnitudes. For every shape, we summed all the magnitudes of their bins into one number. And as you can see here, there's a distribution of shapes going from A on the left all the way to L on the right. And we see this pattern again of the more jagged the edge, the larger the value. And as you get smoother and smoother, right, the values decrease. Okay, same for the bottom 6 objects, G, starting here. G, H, and I are highly jagged, but as it gets smoother, the number drops. Now this panel M, summing all bins for each shape, okay, is just one method of obtaining a scalar value. Alternative methods are to compare only one bin or across all samples, or compare only specific set of bins across all samples, right? As I pointed out earlier here, right, the smoothness of the edge is captured by the last 3 bins. Okay, the smoother it is, the smaller these last 3 bins are. The more jagged the edge, the larger these last 3 bins are. Okay, as observed here too. Jagged and asymmetrical, right, results in larger bins of the last 3 bins. So another way of deriving a scalar value, right, for these upper images, say, or even all these images, is to sum just the last 3 bins. And which bins to sum depends on the system that you are studying, and that is something that needs to be optimized. And alternatively, instead of measuring the full shape, it is possible just to measure partial surfaces. In this case, on the right of each rock image is just the upper half, and we can measure using LCPC just the upper half. And in this case, we would it's probably best to use a parallel grid system instead of the radial grid system, right? And so to just get more coverage of the shape. All right, and so yeah, so this is an alternative way of measuring these rocks: just a top surface, bottom surface, left surface, or a surface, you know, in the same specific objective region in every rock. And there are different different grid systems, excuse me, that would yield cleaner results. For more information and tutorials on how the LCPC transform works, visit our website at brainscanology.com. If you have any questions, feel free to reach out. For consulting services and software licensing issues, please contact info@brainscanology.com.